Hi, everybody. Welcome to this talk on IoT and OT scanning. You might have seen this talk on the schedule with a slightly different title. I changed it at the last minute because I wanted a much cooler visual for what IoT and OT scanning is like. So you are in the right place if you're here to learn about IoT and OT scanning. So my name is Huxley Barbee. I'm the only Huxley Barbee you're ever going to meet. And I am the security evangelist at RunZero. You might know us from our previous name, which is Rumble Network Discovery. We changed our name in August of last year. I am also the lead organizer for B-Sides NYC, and I am really happy to be able to have a chance to speak here at CarolinaCon. I don't get to speak at my own conference, so I have to go to these other conferences to speak, so I really appreciate this opportunity from the organizers of CarolinaCon. So when we think of compute, our minds often go to laptops and servers and databases, and this is what we call IT devices. But this only represents a small number of chips that are manufactured. In fact, I saw one statistic that says 90% of chips are manufactured for embedded devices. Some of these embedded devices are IoT devices, which range in variety. We often like to joke that even coffee mugs and toothbrushes are now on the network. But IoT also includes more run-of-the-mill stuff like printers and cameras, home automation, and power supplies. And some other embedded devices are OT devices, operational technology devices, which operates our factories, water treatment facilities, oil refineries, gas pipelines, and all sorts of areas that our government considers to be critical infrastructure and key resources. Now, 2 points of clarification here. First, I'm using the term OT as a synonym for ICS, Industrial Control System. So if you hear me say OT, you can also think ICS. The second point here is that you're likely to hear about medical devices being referred to as IoMT, Internet of Medical Things. So you might think that medical devices belong to the IoT bucket. However, due to their role in our society and their usage patterns, they look a lot more like OT devices. So in this talk, medical goes into the OT bucket. And in this talk, we will focus on IoT and OT. Many of us are not familiar with OT, so I'll go over that first. And then I will talk about how it's an easy challenge for offensive security to attack OT environments. Then very briefly, I'll touch on what people do for defensive scanning. And next, I will discuss the novel idea of this talk, which is active scanning. And then finally, I will jump over to IoT for a quick look. Even though many OT environments are considered critical infrastructure and key resources, they are shockingly unprotected. But what is an OT device? Well, let's take a look. Well, there is a huge variety of devices in OT environments. It's not like in IT where most people have stock PCs or Macs and all the components are fairly modular. Rather, in OT, there are a lot of devices that are specially designed for certain purposes. And what we walk through here in this simple example is just an example. Just keep in mind that there could be quite a lot of divergence from what I am sharing here. So what we have is a water treatment tank. Contaminated water comes up from the left pipe and goes out the right pipe. You see 2 sensors attached to the right side of the tank. When the water is below the lower one, the right valve closes and the left pump starts pumping in dirty water. And when the water is higher than the higher sensor, the left pump stops. And then after an hour, after the water's been treated, the right valve then opens up and drains the tank. The pumps and the valves are called actuators. Out in the field, you might find integrated sensors and actuators instead of these separate devices. Again, there is a lot of variety in OT environments. The brains of the operation is a PLC. Again, there's a lot of variety in OT environments, so in an electrical plant, they might have IEDs instead of PLCs. IED stands for Intelligent Electrical Device. There's an HMI, which is a panel that a technician uses to adjust the behavior of the system through the PLC. So think of an HMI like a keypad or a touchpad with limited functionality. Just think of your thermostat in your house. It's that type of lockdown interface. PLCs are programmed with an engineer's workstation. This is an actual PC, so it's an IT device in the OT environment, and it is often running an older version of Windows, perhaps even Windows XP. And so what we have here is one system. At a site, you may have multiple of these, all coordinating with each other in what is known as a DCS, distributed control system. On the other hand, you might also have deployments of these OT systems that are spread out over a large geographic area, organized into what is known as a SCADA, supervisory control and data access. With SCADAs, you might have an RTU that allows you to relay between the PLC and some centralized control center back at headquarters. So this is a quick tour of how a small part of an OT environment might look like. Let's now have a look, see how securing OT environments is different from securing IT environments. In IT, we are concerned with movement of data, or controlling the movement of data, or limiting the movement of data. In OT, it's all about moving widgets and gears, moving things around. With IT devices, vendors release products with planned obsolescence, so it is expected that you would replace your tablet, your laptop, your phone every 3 to 5 years. But with OT devices, they are deployed for a much, much longer time. Conventional wisdom in our industry says that the pillars of concern for security are confidentiality and integrity and availability. And arguably, confidentiality is relatively more important than the other two. So think about an e-commerce company. If their site goes down, sure, that's a problem, but they won't get sued or fined for an outage. But if for some reason they were to lose customer PII, well, then they're definitely getting sued or fined. Now with OT, on the other hand, the most important concern is to make sure that there are no outages, right? So let me dig deeper into why availability is so important. So if this is a commercial organization like an oil refinery, then every minute that the plant is down is money lost. So their interest in availability is based on the impact to the business in real dollars. But also, many of these, if they are considered critical infrastructure, can also face fines if there's an outage. For example, when Colonial Pipeline was hit by ransomware and they had an outage, they were fined by FSMA for $1 million. If this is a governmental or a quasi-governmental organization, like a municipal water treatment facility, then there are politicians in power who want to avoid the bad press of outages. So these are some of the reasons why availability is more of a concern with OT environments. Nearly all IT devices run on one of these operating systems, which are all time-sharing operating systems. In OT, you'll find a lot of real-time operating systems instead, and there are a lot more of them. OT devices are programmed with languages like ladder diagram, function block diagram, and so on and so forth. OT devices are almost never updated and never patched. So remember what I said earlier. Availability is paramount. These organizations do not want to shut down for patching or updates. They also don't want to risk a failed update if the risk of a longer outage due to a failed update. Some of you might laugh here that I'm saying that IT devices are secure by design, and I don't disagree with you, but when compared to OT devices, it is true, because with OT field devices, there's basically no security at all. The moment you have access to a PLC, you have access to all the actuators and sensors. OT traffic is rarely encrypted, so traffic interception and modification is definitely a concern. And many OT devices don't even require authentications. And even if they do, there's usually no governance to remediate default users, default passwords, and default settings. So once you get access to a PLC, you own everything. IT devices have endpoint protection, like host-based firewalls, and can be scanned by phone scanners. OT environments in some industries have started introducing security controls and making great improvements, but in other industries, there's basically no security controls at all. Traditionally, IT devices have some connection to the internet, but OT environments were kept separate. And this kind of explains some of the things I said before about insecure by design and lack of security controls, it was okay. Because if you wanted to compromise an OT device, you actually had to walk up to it. Traditionally, OT networks had their own protocols, but starting around 2005, you started seeing more and more of these OT networks getting overlaid on top of IP networks, and thereby reachable from the internet. And that one layer of protection of air gapping OT environments sort of came slowly, gradually falling down. What you have here is the Purdue model. It shows an ideal model of what an OT network should look like, where different levels of risk and controls are stratified for the sake of security. You see the sensors and actuators are in level 0. The PLCs are in level 1. HMIs are in layer 2 and 3. Each layer is supposed to only communicate with an adjacent layer, right? So layer 1 can communicate with layers 0 and 2, but not with layers 3, 4, 5, and 6. Between each layer, there is supposed to be one of two things. One would be physical separation, air gapping. But keep in mind, physical separation doesn't guarantee security. Stuxnet is a great example of how an attack can cross into an air gap environment. And as I said before, this is becoming less and less common as OT networks become accessible from the internet. The second thing that you might find between these layers is some sort of network security control, like a firewall or an IPS that adjudicates access across layer boundaries. But in reality, very few organizations ever achieve Purdue. So if you were able to infiltrate into the higher layers, a secondary attack into the lower layers is shockingly easy. In fact, notice how the top layers are more IT-ish, while the lower layers are firmly OT. Compromising devices gets easier and easier as you move down the stack. The hardest part is actually infiltrating through the top. As you come down the stack, it's much easier to start escalating privileges or moving laterally. And once you do, you move swiftly over to layer 1, and once you're at layer 1, you have access to the crown jewels that are in layer 0. Sounds easy, right? Perhaps? Well, what if I told you that is usually even easier than that? Wouldn't it be easier if you could just skip through all those top layers in that Purdue model and just go right to layer 1 over the internet? Well, yes. The answer is yes, it would be easier. Now, remember what I said earlier. No organization truly implements Purdue. Some organizations are very far from Purdue. And as you can see in this example, we have a PLC, layer 1, a PLC, directly connected to the internet. I didn't even have to log into Shodan for this particular search result. But why bother with Shodan? Why not just use Google with the proper dorks? These days, many PLCs have web interfaces for remote control. So you just log in over the internet. But how do you log in? What's the username and password? Remember what I said earlier. Many PLCs have default users, default passwords, and default settings. It's all right there. In fact, there's a CSV of this type of information from SCADA Strangelove. They're an independent group of InfoSec researchers that are focused on ICS and SCADA. But what if this particular PLC that you're looking at is not using a default password? Well, remember how earlier I said that OT devices are never updated or patched? Just head on over to the CISA website and find a vuln to exploit. More than likely, that vuln has not been patched. So now you might be thinking, well, OT devices are so different from IT devices. Will I need different type of tooling to exploit that vuln? The answer is no. You're good to go with your current tooling. So some of you at this point might be thinking, well, it's time for me to look again to see into my plan of going off grid. But I hope that I also impressed on all of you that there's a problem here with our critical infrastructure and key resources. Any organization with an OT environment needs to have a hard look at it. I was being cynical earlier about why organizations are so focused on availability, but that in no way discounts the importance of availability. Many of our lives depend on a steady flow of electricity or gasoline or pharmaceuticals or clean water. It behooves every security organization to dig into this. Getting a full inventory of your devices is arguably the first step in making sense of this. So how do we find all of our OT devices? Well, some organizations have tried in the past to scan OT environments with active scanners like Nmap or Nessus or Qualys, and these usually result in mass outages and financial loss, which is often not reported. For this reason, security teams usually use a passive network monitor to listen for traffic on switches via taps or a spam port. And as long as you're able to access the appropriate choke points, you'll be fine. But let's take a closer look at this. Suppose you have a SCADA system across multiple sites where all the communication is backhauled through the control center at headquarters. In this case, all the core or distribution switches are on hand at the headquarters, so at least you can see traffic from devices that communicate beyond their site. Now consider a scenario where site-to-site communication is not backhauled through the control center. This is operationally more efficient, but it also makes it much harder to set up a passive network monitor. If you have hundreds of sites, it will be impossible to get a full asset inventory. So by sticking with passive network monitor solutions instead of active scanning, security teams are inviting these issues. They are hard to deploy. Connecting to spam ports or taps at enough choke points is difficult to get done. Passive network monitors collect a lot of data, so you tend to get poor performance unless you have some high-powered hardware appliance. And so as you can imagine, they're expensive. And what do you get for all that money? Well, you can't inventory all the devices because you can't see the ones that are not communicating. The details that you gather are minimal, and fingerprinting is often wrong because you're limited to what you see on the wire. So let's dig into the reasons why active OT scanning has failed in the past. These reasons are also the basis of the 5 principles of active OT scanning. Scanners like Nmap and Nessus are use intentionally non-standard packets or unexpected payloads for fingerprinting. Have a look at packet 2053. This is known as a Christmas packet. Notice how the fin, the push, and the urgent flags are set to true. This is not a standard packet. And depending on the network stack, this might be handled, but what is often the case with OT devices is that they crash, or they reboot, or they freeze up. And the same is true higher up in the stack with application payloads. Programming for IT has had decades of innovation in the way our software is engineered and tested and released, and handling arbitrary input in a robust way through input checking and balance checking is a standard practice. With OT devices, the code was written to respond to someone pushing a button, not arbitrary input over the network. So unexpected payloads can also lead to reboots and freezes. Vulnerability scanners send security probes to detect vulnerabilities. By its very nature, it sends unexpected traffic. For the same reasons as the previous slide, OT devices may react erratically. Legacy vulnerability and network scanners can send large amounts of data or traffic to endpoints in a short amount of time. OT equipment may not have the processing power to handle heavy scan traffic, which causes slowdowns or freezes. But also, sometimes, active scan traffic can be too much for networking devices. So in this example, we have a pipeline in the middle of nowhere where you can't get fiber or DSL. Instead, they have to rely on phone service and a modem. And then you also have a pump that's in an even more remote location. This site has to communicate via radio through the pipeline site, piggybacking over the phone line. This is not the type of network that can support lots of scan traffic. The solution here is to make sure that you tune your scanner in at least 2 ways. First, by dialing down the total number of packets per second from your scanner. The second is to spread out the scan traffic across multiple devices. So rather than hitting each device sequentially with a ton of packets, instead you actively scan multiple devices at once, but less traffic to each device at any given time. Number 4, there are some devices where even standards compliant traffic can crash them. To handle these, it's important to avoid the type of fingerprinting you might find with Nmap or SynFP, where you try to capture all the necessary information at once. Rather, you start out with some super benign query to get some idea of what you're working with, and then you iteratively follow up with more in-depth queries when you know it's safe to proceed. The last principle here is to go slow and start small. And let's move on to IoT. One major problem with IoT scanning is they tend to have few listening ports, and they tend to be encrypted. So when all you see is an SSH port and an HTTPS port, it's tough to figure out what something really is. For that reason, naive scanners often identify IoT devices as just Linux boxes with little detail on what the thing actually is. Is it a coffee mug, or a lava lamp, or a washing machine, or is it a power supply? No idea. It all just looks like Linux. If you start looking deeper, you might be able to see the IoT platform that the device was built on, but you're still not getting a good sense of what the thing is. Fingerprinting IoT often involves a painstaking process of actually looking into payloads to find model-specific information that tells you what something is. And oftentimes this means contacting the device via HTTPS and parsing the response for telltale signs. Many IoT devices are prone to disruption as well. Similar to OT devices, they are coded to respond to buttons being pressed or somebody plugging something in. They are not tested to handle arbitrary input of strange network traffic. Again, like OT, there are devices that behave strangely, even with standards compliant traffic. Examples of this include serial to Ethernet connectors or print servers. In fact, we've seen printers out there that where if you send certain traffic on port 9001, it just starts spewing out paper. Now, right now, you might be thinking, okay, this isn't a big deal. Disrupting a network-enabled coffee mug just means you get a bad cup of coffee. But keep in mind that many of these IoT devices are valid attack vectors into our homes and businesses and have real impact on privacy. And it's no surprise that some of these devices are restricted under the National Defense Authorization Act, Section 889, which addresses a very real threat. I personally know of at least one organization that found an IoT camera that was making network connections to an IP address in China. Right? This is a Section 889 type of device. It was making a network connection to an IP address in China, even though they don't do any business with anyone in China. I'm sure there are many, many more instances of this. So it's important to get out there into your environments and figure out what you have on your network. The good news is the same 5 principles that we discussed for OT also work for IoT. So here's the parting thought. There was a time where you wouldn't do any of these things, but now you get into Ubers, you buy crypto, you all work from home. So maybe it's time to start considering doing active scans in your OT environment, governed by the 5 principles that I discussed earlier. All right. I would love if you all would connect with me in whichever way you like to connect. You can email me, or you can connect with me on social media. And also, there's some links over here on the right if you want to learn more about OT security. Thank you.